Okay, so today we're going to be solving this question related to unit B.2. It is actually quite a tough question. It's worth quite a few marks as well. It's worth 3 in part A, 3 in part B, 1 in part C, 2 in part C.2, and then another 2, but the last 2 are not relevant to B.2, so we would be skipping the last part of the question. But let's go. So the question says a solar heating panel is placed on the roof of a house in order to heat water in a storage tank. The rest of the roof is covered with tiles. On a certain day, the intensity of the solar panel that is incident perpendicular to the surface of the panel is 680 watts per meter square. So the following data is available, and it lists out the data here. And determine the minimum area of the solar heating panel required to increase the temperature of all the water in the tank during to 30 degrees Celsius during the time of 1 hour. So, firstly, from our formula booklets under B.1, we know that thermal energy needed to heat, Q, is equal to mc delta T, where m is mass, C is specific heat capacity, and delta T is change in temperature. So first we have to find Q, the energy required to change everything from 15 degrees Celsius to 20 degrees Celsius. So Q will be 250 kilograms of water times 4,200, or the specific heat capacity of water, times the change. So that'll be 30 minus 15, or which is 15, so we can just write it as 15. Entering this into your calculator will give you about 1.58 times 10 to the 7 joules of thermal energy required to raise the temperature. So next what we have to do is we have to find the thermal energy that will be absorbed. So we know that the efficiency is 0.3. So let's quickly write that down. Times the intensity, which is incident on the solar panel. It says that it is 680 watts per meter square. So that is 680. And now we multiply this by the area to get the power. And then we multiply the power by the time to get the energy. So the time here is 1 hour, which is the same as 1 times 60 times 60, as that now gives it to us in seconds. And we equate this with this. Equating these two expressions and solving for area, you get 21.44. So you have 22 meters square as the minimum area required. So part B says estimate in degrees Celsius the temperature of the roof tiles. Alright, so we know here that the albedo of the roof tiles is 0.2. So that means 0.2 is equal to the power scattered over the power incident. If we multiply our value by 1 minus 0.2, we get the power which is being absorbed. So power absorbed over power incident. So the absorbed intensity is what we will get. So multiplying 680 by 0.8, we get 544 watts per meter square. With this value, we can now say that 544 will equal to the Stefan-Boltzmann constant times the temperature of the tiles to the fourth power times the emissivity of the tiles. The reason we don't have the area A is because this has a unit of watts per meter square, and we know that power is equal to emissivity, which has no units, the Stefan-Boltzmann constant, the temperature, and the area. So if we divide the watts by the area, we know, as power is directly proportional to area, if we divide watts by the unit of area, which is meter squared. We get watts per meter squared, which is the unit of intensity. So that's why we don't need an area. We've already divided by it. So now we just have to substitute in our values. 544 equals 0.97, which is the emissivity, times the Stefan-Boltzmann constant, which is given in the formula booklets, is 5.67 times 10 to the negative 8 times t to the 4. And if we just rearrange for this and solve for t, we get that the temperature of the roof tile will be 1 second. Will be 315 Kelvin. So this, it asks for it in degrees Celsius. So we subtract 273, so 315 minus 273 equals 42 degrees Celsius. So now part B says there is an airspace above the water in the storage tank with an opening to the atmosphere. Assume that the air behaves like an ideal gas. State one way in which a real gas differs from an ideal gas. Alright, so a real gas has intermolecular forces between the particles like this. So there'll be attractive forces between the particles. But in an ideal gas, there are no intermolecular forces between the particles, as the internal energy is made up solely of the kinetic energy of the particles. So the reason it differs is because an ideal gas has no intermolecular forces. Alright. So it now says that the airspace is always at constant atmospheric pressure and constant volume as the water level is kept constant. The airspace temperature and water temperature are the same. The water is heated. Explain why the quantity of air in the storage tank decreases. Alright, so we know that volume is directly proportional to temperature, and this is given at constant atmospheric pressure and constant volume. So if the volume of the air increases and the total volume must remain constant, it means that some of the air has escaped the container in order to make because air expands under a higher temperature. So in order to keep volume overall the same, some air must leave the tank, otherwise the tank would explode or it would break open. We don't really know. So that's why the quantity of air in the storage tank decreases, because the air that has been in there has expanded and some of it has left the tank, so there's less air than there was before. So I hope you found that helpful, and subscribe. Thank you.